Synthesis, the skills, materials, and decision-making involved. These are the key concepts that we'll be covering in this video. Synthesis reactions can be broken down into 4 key steps. The first step is the actual reaction. Moving on, we need to isolate our products, and then we need to purify them, and finally, confirm the identity and purity of our end samples. Part 1. React. How do we measure our liquids, our solids, and what types of glassware will we need in this reaction? Is accuracy important? Measuring solids. We can get an approximate mass, and accuracy doesn't really matter as this is synthetic and not analytical chemistry. The goal of synthesis is a pure, targeted end sample. We can use weight by addition in this example instead of using weight by subtraction, which is more precise. We'll need a beaker, a spatula, an analytical balance, or any type of scale really, and we'll need to do this for both ethanol and the ester. It's also important to note that sodium hydroxide is extremely hygroscopic, so we need to do this quickly and close off samples possibly with the lid. Likewise, when we're measuring liquids in synthetic chemistry, we don't have to pay as much attention to how accurate or precise we are. We can get approximate volumes. Here for ethanol. The goal of synthesis is a pure, targeted end sample. We'll be using a measuring cylinder. Although pipettes are more accurate, a measuring cylinder in this case will suffice. So we're moving on to reaction and glassware. The reaction involved in this experiment is a super ambient reaction. So that means it involves a lot of heat. So we'll be heating, or rather boiling, our ethanol and adding sodium hydroxide to it to get our end product, which is the carboxylate, plus a side product, which is the alcohol. So we'll need a round bottom flask, a condenser, and a hot plate. The great thing about a round bottom flask is that there's even heating throughout the entire solution. It's durable due to that rigid, egg-like structure. We'll need a condenser because we'll need to eventually capture the evaporating solvent, recondense it back into the reaction flask. And of course we need that hot plate as a heat source. You can use any heat source really, but in this case hot plates are quite conventional and more appropriate here. Right, so stepwise setup, the reflux apparatus. First we need to insert our reactants and our solvent, our ethanol, our sodium hydroxide, prior to heating, into the round bottom flask. Then we need to loosely clamp around the condenser. It's important that we aren't too tight with it, otherwise it might actually crack the glassware. We also need to clamp around the neck of the flask. Then finally, we need to set the hot plate above the boiling point of ethanol. It's important to note, and actually quite interesting, that the reflux will never heat above the boiling point of solvent. Another thing to be cautious about is that you should never place a stopper on the condenser. That heat needs to escape somewhere, so there's a possibility that the glassware might actually explode or crack due to that pressure buildup, as all of that energy and heat has nowhere else to go. Potential hazards. One of the risks involved in this experiment is actually burning and scalding. You know, reheating the ethanol, it's being boiled to a very high temperature, and who knows, you might actually touch the hot glassware and burn yourself. There's also intoxication, you might actually consume the ethanol. Flammability and volatility. Ester and ethanol both are very flammable and very volatile, so they have that low flash point, which means that they can actually evaporate quite readily and easily. Finally, we have the corrosive sodium hydroxide that might actually cause some serious damage to the eyes and respiratory system. Confirming that the reaction is actually complete, we'll be using thin layer chromatography, also known as TLC, which basically separates molecules by their affinity to polar silica, the stationary phase, versus mobile phase, the mix of organic solvents, that's the non-polar phase. So polar compounds that are attracted to stationary phase will move less up the TLC plate than non-polar, which are attracted to the mobile phase, and will move faster and higher up the plate. In this experiment, TLC will allow us to differentiate between the reactants and the products. Spots of ester solution will have a different color and retention factor than the carboxylate. Now that our reaction is complete, we'll know once each dot stops moving up the TLC plate. It's also important to note that we will need to use UV light here, since not all solutions are actually visible when dotted on a TLC plate. Isolation of product. Carboxylate is actually more water soluble than the methanol, so we'll really need to capitalize off of this difference in polarity. Now, we'll need to isolate the polar segments from the non-polar segments. The methanol will dissolve in non-polar solvent, the diethyl ether, which we can use in this case, and the carboxylate will dissolve in the polar medium, which is the water. Liquid-liquid separation. Step 1, set up the separating funnel. Combine the organic solvent, in our case diethyl ether, with our reaction mixture, which was the methanol and the carboxylate, transfer the solution to separating funnel using a glass funnel, add sodium hydroxide to extract it, stop at the separating funnel, and invert repeatedly, occasionally opening the tap to release the pressure, then collect the aqueous layer first. Repeat the sodium hydroxide extraction, and finally wash the crystals that we get with water and collect the organic layer. Purification of product. We're using recrystallization to purify our sample. The first step is to cool the aqueous solution over an ice bath. Add an acid that will actually precipitate out of the solution. Continue adding the acid until the pH is around less than 7, so an acidic range. We can use litmus paper to check that. Collect the crystals in a Buchner funnel, evaporate off the water in the crude acid solution, collect the crystals with a Hirsch funnel, and cool it in ice once recrystallization appears to be complete. Finally, wash and dry at the pump with water. Analysis of product. Infrared spectroscopy. Basically, we radiate a sample with infrared light that reaches a detector and passes some light through some sort of sample. Now, some of that light will be absorbed and the other will simply pass through it. There will be particular movements or stretching that depends on the functional groups present in our solution. So why are we using IR spec to identify and analyze our sample? Carboxylic acids actually have a very broad, unique stretch that you see within 2300 and 3400 wave numbers. IR spec allows us easily to spot these. Now, each carboxylic acid and all the other derivatives of carboxylic acids actually have a specific and exact frequency of that stretch, which can actually differentiate them from each other. Now, a table of values that you can easily find online can actually identify where each of these stretches happens and for what carboxylic acid. So, using that table and all that information online, we can easily analyze and identify whether our final solution in its purified form is what we are aiming for.